Moving forward with problem number 32, we have a continuation of what was going on before. We have our spherical balloon is back, okay? And this time we're told that the volume of the balloon is increasing at 100 pi cubic feet per minute. Now, we're not specifically told that. We're told that the balloon is being inflated at this rate. Okay, that's just using our intuition to realize that, hey, the inside of the balloon, the volume of the balloon is changing, it's increasing. And the rate at which it's increasing is 100 pi cubic feet per minute. Okay. We need to assign this value to a particular variable. All right, and hopefully, as you're seeing these and doing them more and more, we can see that, hey, we got the units, we got volume units, we got cubic units over time. So this is dV dt. All right, so dV dt, we're told, is 100 pi. Okay, that's our given. And we got two parts to the question. And part A is asking, what rate is the balloon's radius increasing? Okay, radius changing, radius increasing, so that means we're looking for dr dt. All right, we're trying to find out what dr dt is, but we're specifically told that r is equal to 5. All right, so now we have two values and what we're looking for. So we've taken care of the understanding the problem. I'm going to skip the drawing the picture again, but I think we'll do that on the next example. So now it's time to write our equation. We know that the volume of a balloon is 4/3 pi r cubed. And we actually already found the derivative of this in the previous video. So we know that dV dt is equal to 4 pi r squared dr dt. Again, if that's confusing to you, just refer back to example number, I believe it was example number 29, maybe example 30. Okay. So what do? We're plugging in our values. We have 100 pi, which is going in for dV dt. We have 4 times pi times r squared, and we know that r is 5. So 4 times pi times 5 squared. And then we're trying to find what dr dt is equal to. All right, so here's dr dt right at the end, at the edge of our screen there. Okay, well, what's 5 squared? 25. 25 times 4, 4 quarters make a whole, so we have 100 pi here. So we can divide both sides by 100 pi. And that'll eliminate everything on the left side and almost everything on the right side. So we're left with 1 is equal to dr dt. All right, and specifically if we're looking for units, all right, we know that our distance is in feet, and so we're looking at feet per minute. So I'm actually going to move this over just a touch so we know that the radius is increasing at a rate of 1 foot per minute. Okay. Now, part B says, at this exact moment, what's the rate at which the surface area is changing? All right, so we need the formula for the surface area of a sphere. Surface area of a sphere is 4 pi r squared. And if we find the derivative of the surface area, right, we're going to have ds dt, because surface area is going to be just like volume and just like area from the previous problem. It just derives to 1 times the derivative of surface area with respect to time. Over here on the right side of the equation, the 4 and the pi are coefficients, so they're going to stay. But r squared is going to derive to 2r dr dt. Okay. And now we can plug in again. We know that at this instant the radius is 5 feet, and we just solved that dr dt is 1 foot per minute. So when we sub in here, we have 4 times pi times 2 times the radius, which is 5, times dr dt, which is 1. And if we put all of that together, 4 times 10 is 40. So we are looking at 40 pi. And if you want units, well, now it's surface area. Area, surface area, that's in terms of square units. So this will be square feet per minute.